Imagine we have a bridge which is shown in this green color over here, and it is somewhat supported by these things, this little support over here, this triangular support, truss support over here. Alright, so this bridge is somewhat supported, and it's a very busy bridge and having tanks moving along this bridge, lorries moving along this bridge, and things like that. Eventually, a long time, the bridge itself may actually deflect, and this deflection is shown in this red outline over here, right? This red color one, if I were to color it. So after certain time, maybe 30 years, this bridge actually deflected permanently in this red color one, as you can see, right? And as time goes by, things may actually happen, and the bridge might not be able to support cars or heavy loads in the next 30 years or so, I think. And apparently in finite element, you want to actually look at what is the greatest deflection, and definitely where is the deflection going to occur. So we're going to talk about the coordinate system. Alright, if your bridge is somewhat maybe 1 meter, alright, if your bridge is 1 meter, then at least you would know that, okay, this is somewhat maybe perhaps 0.55 meter, right, at this greatest diffraction. Where's my pen line? The greatest diffraction maybe occur in 0.55 meter somewhat, alright, but if it's 1000 meter, then it's very tough to actually determine what is the actual coordinate at this region, right? At this region over here. So we are actually kind of keen of the coordinate system itself. Which coordinate is the most deflection occur, and things like that. And this is, I believe, the reason behind what we're going to study, which is continuum mechanics. Alright, continuum mechanics itself, it's by far, it is considered a continuous body, meaning it does not break. Alright, for example, by definitions, a continuous body itself, if you take a look in this soccer ball, right? If you were to go into, if you just look itself, it is in fact a continuous body. But if you were to zoom in 1000 times, if you were to zoom in, you will see particles, atoms, right? And they aren't actually together, right? They have some distance apart. So in the continuum mechanics, it is assumed that the whole spherical soccer ball is somewhat, all the atoms are packed together, alright? There's no discontinuities, right? So this is the discontinuities. So we are not actually keen. We are actually assuming that the whole thing is in terms of there's no discontinuities, where these discontinuities may be like some cracks along the section, alright, cracks. As I said, the atoms itself has some spatial space apart. We are actually ignoring that. So this is by far the continuum mechanics, and therefore this is used to actually help us to define certain things in the finite element. Alright, I don't know why am I lagging, I can't write properly. Yeah, in terms of finite element. So in terms of finite element, there are a few stuff like the truss structure, the beam, and so on and so forth, right? And therefore this continuum mechanics set as a basis for us to actually look into the finite element stuffs over here. And therefore this is somewhat the introduction to mechanics, and I shall see you in the next video for other stuff.